In this lecture, we're going to look at the reactions of organometallic reagents with carbonyl compounds. First, let's define what organometallic reagents are. All organometallic reagents contain a carbon to metal bond, which gives the carbon a partial negative charge and the metal a partial positive charge. From general chemistry, you might think that a carbon-metal bond would be ionic, but actually it's polar covalent, which allows organometallic reagents to dissolve in organic solvents. Now, the first class of organometallic reagents we're going to consider are the Grignard reagents, which are very famous. They're used to make a lot of organic compounds. The general structure of the Grignard reagent is RMgX. R can be an alkyl group, such as methyl, ethyl, propyl, or a carbon-carbon double bond. X is either chlorine, bromine, or iodine, and you react that with magnesium metal, not magnesium cation, actual shiny magnesium metal. Okay, you stir that around in the appropriate solvent, which would either be diethyl ether or THF, tetrahydrofuran, and that'll generate the Grignard reagent RMgX. So, for example, you could take methyl iodide and react that with magnesium metal, which you shined up, ground up so that's a nice exposed surface of magnesium, and that's going to be stirred in ether. It's an exothermic process, which would generate methyl magnesium iodide, CH3MgI. Note that the carbon has a partial negative charge, and magnesium has a partial positive charge. What happens in this process is that the oxidation state of the carbon goes from +1 in methyl iodide to -1 in methyl magnesium iodide, which means it's gained 2 electrons. That's a reduction. The magnesium, in contrast, starts out as a free metal. Okay, and remember, all elements in their free state have a 0 oxidation state. So it starts out at 0. It gives up 2 electrons, or loses 2 electrons, to form Mg2+. So that's an oxidation. So the formation of organometallic reagents, including Grignards, is an oxidation reduction process. The carbon gains electrons, the metal loses electrons. In the bottom example, we have bromobenzene reacting with magnesium, and this time we're using THF as our solvent to form phenylmagnesium bromide. You can see that the carbon connected to the magnesium is partially negative, magnesium is partially positive. Organolithium reagents have the structure RLI. They're very similar to Grignards in their reactivity. What happens is that you combine an RX, again an alkyl halide, or vinyl halide, where you have R as alkyl or C double bond C, X is Cl, Br, or I, now with 2 equivalents of lithium to form RLI, the organolithium reagent, plus the salt LiX. The solvent typically used in these types of reactions is hexanes, and here are a couple of examples. If you take methyl iodide and 2 equivalents of lithium, you'll get methyl lithium plus lithium iodide. Note that the carbon has obtained a partial negative charge because it's bound to the metal lithium, which is partially positive. That is the polar covalent bond, which allows methyl lithium to dissolve in organic solvents. If you use bromobenzene and react that with 2 equivalents of lithium, you'll get phenyllithium plus lithium bromide, and you'll have a partial negative charge at that sp2 hybridized carbon bound to a partially positive lithium atom. As with the formation of the Grignard reagent, the formation of an organolithium reagent involves an oxidation reduction. The methyl group in methyl iodide has a +1 oxidation state on carbon that gains 2 electrons from lithium to form a negatively charged carbon in methyl lithium. So that has a -1 oxidation state. The lithium starts off as a free element, a free metal, 0 oxidation state, and each lithium atom loses 1 electron, 1 lithium binding to methyl groups to form methyl lithiums. That's a +1 oxidation state for that lithium. And the other lithium as part of lithium iodide. So that's a total of +2, and we started at 0, so that's a loss of 2 electrons. So what destroys organometallic reagents? What should you keep them away from? Definitely water, okay? Anything that contains an OH group is going to transfer that proton to the organometallic reagent and destroy it. So compounds containing acidic protons like OH are not acceptable. You have to make sure they're not in the reaction. You need to keep the solvent and the glassware dry. So that means usually oven drying the glassware before you use it, making sure that the solvent has been dried by some means, such as using a drying agent before you use the solvent. When the Grignard reagent RMGX reacts with something with an OH group, and the example that I'm showing here is an alcohol, the proton, the acidic proton, transfers to the negatively charged R group, and you get RH. Okay, and you also produce the salt R'(O)MgX, and a lot of heat. One of the effects of having a Grignard, if you have any Grignard at all, reacting with traces of acidic protons, is you generate an exothermic reaction, which can potentially be explosive. So you really have to be very careful about this. Now the organolithium reagent is very similar. The partially negative R group picks up a proton from the alcohol, again forms RH, and the salt, which is now a lithium salt, R'(OLI), and a lot of heat. So just another reminder, keep these reagents away from water, keep your glassware and your solvents dry. Otherwise the entire process will fail, and it could fail catastrophically. Okay, let's look at the simplest example of the reaction of an organometallic reagent with C double bond O, and that would be the reaction with CO2, carbon dioxide. So if we have a Grignard reagent or organolithium reacting with CO2, in the overall reaction we follow that with dilute acid to form a carboxylic acid. And in our mechanisms, what we want to do is take the Grignard reagent and stack it over C double bond O, such that the partially negative R group lies over the partially positive carbon, and the partially negative oxygen in C double bond O is lying underneath the partially positive magnesium ion. And you can see that more clearly with the resonance structure. So partially negative R is going to transfer to the C+, and partially positive magnesium is going to get picked up by O-, forming our initial salt. Then in the second step, we protonate that salt, which breaks the oxygen-magnesium bond, forming our carboxylic acid and releasing magnesium ion and the halide X-. It's very important that these are two separate steps, because as we've already learned, if there's any source of acid present, that's going to destroy the Grignard reagent. So you have to let the Grignard reagent do its job first to form that bond to carbon. Then you get to add the proton onto the oxygen in a second step. Now with organolithium reagents, the mechanism is similar. Again, you stack the partially negative R group over the partially positive carbon, and the partially negative oxygen is going to interact with the partially positive lithium ion. You'll exchange the pieces. So now R is attached to C+, and Li is attached to O-, forming a lithium salt. In the second step, we protonate the oxygen, forming our carboxylic acid and releasing the lithium cation. Okay, now on to the reaction with aldehydes and ketones. In that situation, a Grignard or organolithium reagent reacts with C double bond O pretty much the same way it did with CO2, followed with dilute acid to form not a carboxylic acid in this case, but an alcohol. So you notice the red R group is what attaches. You get one attachment, one new carbon-carbon bond. If you started with an aldehyde, then you get a primary alcohol, and you've started with a ketone, you get a secondary alcohol. So looking at the mechanisms of this reaction, you see that the Grignard again does the same thing it did before. It lines up with C double bond O. You can draw a resonance and note that the partially negative R group will now transfer to the positive carbon, and the magnesium ion will transfer to the O minus, giving you the salt, which we would then, in the second step, decompose with dilute acid to form our alcohol, releasing magnesium ion and our halide. As before, the organolithium reagent is going to line up with C double bond O. You're going to transfer the partially negative R group to the C plus, and the lithium cation to O minus. And once you form that salt, you follow that up in another step with dilute acid, generating your alcohol and releasing the lithium cation. Now for the reaction with esters. It takes two equivalents of either a Grignard reagent or an organolithium reagent to react with an ester, because we're going to make two carbon-carbon bonds. The OR prime group in an ester is going to be our leaving group, and that's going to be displaced. So overall, two equivalents of RMGX or two equivalents of RLI will react with the ester, followed by a second step with dilute acid to form a tertiary alcohol. Notice two R groups, two red R groups are attaching to the carbon. Now that can also be secondary if R prime is a hydrogen. But typically it's tertiary. But if R prime is a hydrogen, it's secondary. So mechanistically, the Grignard is going to, as before, overlap with C double bond O. We're going to transfer the partially negative R group to the carbon. The magnesium gets picked up by the oxygen. Now, what's different from the aldehyde and ketone case is we have a leaving group. So R prime O is going to get kicked out by the negative charge on the oxygen coming into the partially positive carbon, and that will displace, knock out R prime O minus. That gives us a ketone. We've already seen that the ketones react with Grignard reagents. So that means the second equivalent of Grignard's going to go after that ketone. It's not going to just be able to sit there. It's going to get attacked again. So that's what we show in the bottom line. So Grignard goes after C double bond O. The R group attaches to C plus. The magnesium attaches to the O minus. Now we don't have any more C double bond O. So we can stop at this point in terms of reaction with the Grignard reagent. And we can follow it up by the second step with dilute acid to produce our OH group and thus our alcohol. So here's the key thing. There's an intermediate ketone in this reaction. Ketones react with Grignard reagents, so the reaction can't stop. It has to keep going until there is no more C double bond O. Until you have a single bond between carbon and oxygen, then the reaction stops. Once that happens, you get to protonate that oxygen with dilute acid to form your alcohol. So again, remember, don't bring in that H3O plus until you've already used up all of the Grignard reagent. It should have delivered both R groups. Then you can add in the acid in the mechanism. Now notice I'm not even showing you the mechanism with the organolithium reagent because I want you to figure that out in a practice problem. So here it is, practice problem 1. Draw the mechanism of the following reaction. Yes, indeed, there is no organolithium reagent in this reaction with an ester to form a tertiary alcohol. So just use what you learned about the reaction of a Grignard reagent with an ester to figure this out. Okay. At this point, you want to pause the video so you can work on this mechanism and then check, and then let the video continue and to check out what the answer is. Okay, here's the answer to practice problem 1. Okay, we're going to take the phenolithium and we're going to stack it over C double bond O, transfer the partially negative phenyl group to the carbon, that's positive, and the partially positive lithium to the oxygen, it's negative, and form our intermediate that's unstable. Electrons flow from the OLI bonds, basically O minus, to the partially positive carbon and kick out the oxygen leaving group, which will now have a negative charge. We generate our ketone intermediate, and lithium cation and our ethoxide anion. Now that ketone is going to react again with the second equivalent of organolithium. So again, we stack. The phenyl group transfers to carbon, and that gives us our new carbon-carbon bond, our second new carbon-carbon bond. Oxygen will pick up the lithium ion again, and in the final step, we protonate the oxygen to generate our tertiary alcohol and release the lithium cation. Practice problem 2. Predict the organic product or products of each reaction. At this point, you want to pause the video to give yourself time to work on these problems. Answers to practice problem 2. All right, in the first reaction, problem A, we have an aldehyde at the end and a ketone at the beginning. We have an excess of methyl magnesium bromide. So that means that we're going to react at both C double bond O's. We have enough Grignard to do that. And they're going to react at each C double bond O once, right? Because we don't have a leaving group. These are aldehydes and ketones. So we get one red line at each place. Okay, one methyl group attaching to each carbon. So we get a tertiary alcohol at the beginning part of the molecule from the ketone, and a secondary alcohol from the aldehyde. In part B, we have the reaction of carbon dioxide with an organolithium reagent, shown in red. So that's going to form a carboxylic acid when we follow that up with H3O+. In part C, we have both a ketone at the front part of the molecule and an ester at the terminus, the end of the molecule. We have an excess of phenyl magnesium bromide, so we have more than enough Grignard to react. Okay, and you'll always get more than enough, because if you try to stop in the middle, you just get a bunch of junk mixtures. So you have enough of this phenyl magnesium bromide to go after both the ketone and the ester. How many times does it go after the ketone? Once. So you get one phenyl group attached to that carbon. And how many times does it go after the ester? Got a leaving group, right? So it goes after that twice, right? Once to displace the leaving group, the methoxy, the OCH3, and once to break the carbon-oxygen double bond. So you get two phenyl groups on the end. And in part D, now we're actually going to make a Grignard. We start with this vinyl bromide, or alkenyl bromide, if you will, which reacts with magnesium and ether. And that then is going to react with the ketone, which this specifically is acetone. So that's going to attach once to form our tertiary alcohol once we protonate it with H3O+.